So we're gonna show you guys today active contours. I'm Diana, this is Jose.
Yo.
So first, we're gonna talk about priming. So there is a reason why we put this here. This is something that psychologists use to put something into context. So before we explain this active contours, we want to show you some examples so you can put everything into context. And this is just one example of it. If I tell you this is a button, then you can say, okay, this is a button. But if we tell you that this is a person in a bicycle with a Mexican hat, then you start seeing as like that. So that's why we need some information before we go into this. So what are active contours? They're used for many applications, including object tracking, shape recognition, segmentation. So this is just some examples of it. You have this picture of the monkey here, and then we just have some lines around it, and then with the algorithm we are able to track the shape of the monkey. Also used for edge detection. You can see also this example here. We have this shape, and then we can get the contour of the player. So just it's used for many things, and this is some examples that we're going to show you. Okay, one example is this actor animated cat. So how it works is that the algorithm tracks the shape of the mouth and some of the facial expressions of the actor, and then the animation will copy the expressions of the actor. So if the actor opens the mouth, then the cat will also open the mouth. The actor is showing an angry face, and the cat is going to be showing the same thing. Also used for tracking monitoring. Because this is a highway, the cars will have very traditional, I guess, route. So if you see something that is out of the ordinary, maybe there is an accident there, or maybe there is a traffic jam because you see a lot of the squares. So this is just some of the examples. You can easily spot any anomaly in the traffic. Now, this is another example is a robot tractor that is just camera it shows it has a camera and has some sprayers, and then it can recognize because of the shape of the plant, it can recognize which is the plant that is going to have fertilizer, where is the ground and where are the weeds. So it's just going to spray some stuff to kill the weeds, and then put some fertilizer on the plant and distinguish from the soil. So this is another example of how we can use contours. Also a robot with hand-eye coordination. So we have a camera here, and then the white spots that you see here is basically where the robot is going to grab the screwdriver. So we will draw a line here, and also another example. So there are many examples. Surveillance. We have this camera here, and then let's say the camera gets activated whenever it sees like a human shape form. You don't want to have the camera maybe recorded get activated every time the cat or the dog walks by. So this is also a very useful example. Another example is body motion. So this is used for movies and to create animations, and it's also used to track how the body moves. So if someone is training, some athlete is training, and if it has some injury, so they're tracking how the movement goes. Another example how we can use active contours. And also here there is this new software from Adobe that can track how you move your lips, and so we want to show you an example of this. Let me pull up the video. So you can see how this person, how he moves his lips and his facial expressions. And then the target here would be the president, and you can see how he moves his lips too. Okay. So let's continue. Now we're going to show you some methods for active contours.
So the first method we'll talk about is the level set. So level set is the general a quick explanation of level sets. We have our shape represented by a function phi. And so a level set is just a cross section of our function phi at a time interval or iteration. So when our iteration goes to 1, our phi function shifts and we're trying to get the cross section where our x and y equals 0. So here's this is usually most images are represented as a planar curve or just an equation of a line. We want to have more of a mathematical representation of this, so an implicit form of it. So we still have our same duck shape object, and where things on the outside are less than 0, and things on our values on the inside are greater than 0, and everything along the curve or the outline of the shape is equal to 0. So when we do a cross section of our object, we can get our representation of our object where every value outside is less than 0, everywhere or our line cross section hits the line of the object is equal to 0, and everything on the inside is greater than 0. And this is represented by our simple equation right here. So here's some additional functions you use when trying to do level sets. Our normal function is represented by a gradient of our phi divided by our magnitude of our gradient of our phi. And our tangent function is it's going along the curve at perpendicular angle to our phi function, our gradient of our phi over our magnitude of our phi. Make sure additional functions used when trying to define a level sets. And our dv is our divergent function, I believe. And here's the simple mathematical representation of what's going on. What's our function? And remember, George trying to set a equal to 0. So our CSS, I believe, is our second derivative of our curve function. And here's some additional mathematical representation. As you can see, the comparison between our curve function and our implicit function phi, how they're related to each other. And here's we're going to go to an example real quick. And so we plot a function called the Rosenberg function, as you can see. And so right now it looks like just a map, but when you rotate the object, you can see our actual function graphed and represented. So when we take our level set or our function, we can get this. We're cutting our object at some point in tool. And when you get this code, yes, it's important to understand we have to get, when inputting which section of our graph we're trying to cut, or just take our value equals to 0, just give it an array. That's why when we see at the top, I provided an array between 200 and 201. And this is just our cross section. Right now it doesn't seem, it makes a lot of sense, but when compared to our previous plotted image, you kind of see how this part of the image is curved, and so it's on the interior portion. And so our cross section right here is two parts on a level. So on this portion, which is represented right here, and on the interior, I guess, heel, where is this part? And so, what happens when we change our array? Any thoughts? Our input array, of what section we're trying to cut from our plot? No answers? Well, depending on the array, you can cut multiple layers. You can cut at different heights, and you can cut multiple times, so get different level sets at the same as our output. That's pretty much what happened. You can test it when you have it. It's level right there. Our input array, and now you have it labeled to change the array. So you can change the array between 0 and 800 at increments of 50, and it will plot every level set along those increments. You can also plot using the exponent function to give you an exponential growth of all our plots. And so if you're trying to research the level sets, you might come across this simple representation of our level sets. It's very similar to what we previously showed you, where our Vt is our first differential with respect to t, and our h variable is a Hamilton equation, which I won't go into detail because it goes into quantum mechanics, which is mathematics. So that's why I just provide a nice little simple equation. And so with our level set, when doing computation, sometimes we want to do a larger sample size. So that's what narrow bands comes in. Narrow bands, we're taking our level set, but we're broadening it out and taking a section of our object at a time. So we're trying to go expand outwards. We're expanding to, I guess in this situation, to the -3, +3 increments. So as we grow out, or we go up in increments, it's a larger width. I'm taking, I believe, the average of this section plot.
So now we're going to talk about the fast marching method. So the mathematical basis of this is actually quite complicated. So we're not going to go really depth into it. But for what I understood, this method is very similar to how do you pronounce this thing? Dijkstra? Dijkstra? Equation, algorithm.
Just skips a G.
Sorry?
Just skips a G.
This Dijkstra? Thank you. Okay. So it's very similar to how this algorithm works. So I made this little example of how this algorithm works. So we want to, we're in node A, and this is our initial point, and then we want to get to node F. So what the algorithm does is sets all the other nodes that is not the initial node as infinite. And then it sets this initial node as 0. Then it starts taking the value, this distance here, which is the weight between the nodes, and then it takes the path with less weight. So it will go from here to here, and then the weight is 1, because this weight is 1, it's going to put it here, and then because this one is 4, it's going to put it here. Then next, it takes because it took the one with less value, then it produces the same. Now it goes from here to this one, and the weight is 2, so it changes this value to 3 instead of 4, how it was before here. And then it moves this one to this one. This path is 10, which just symbolizes a longer distance, for example. And then it's going to give this node a value of 3. The reason why 11. The reason why this is 3 is because it actually adds the whole path. So we go through the same point, we move this one, we make the current node 3, and then again, we give this one the weight of the whole path, and this one too. So this one's going to become 6, and this one 8. Now the next step, it's going to take this value, and then calculate the next nodes, and then this is the last node, and of course the smallest value is this way, so it finds the smallest path. So this is the algorithm. Actually, we found it on this paper here, that we found that it explains really well how this method works, and that's why we wanted to use it here. So the idea behind this is that we're going to have one pixel, which is going to be the red one, and then with the equation that we showed you before, it calculates the values of the neighboring cells of this initial point. And then it's going to get the smallest value and then calculate again the neighboring values. And then it's going to find the smallest points and then expand until it's done with the whole equation. Now we're going to show you another example, also with the fast marching method.
You have a question?
Yes.
Yeah. Can you? Okay, no. Don't worry.
This,
Yeah, let us finish with the
presentation?
code. Let us finish with the code. After that, I will.
Okay. So let me show you an example. Might even solve your question. Okay.
Yeah.
So we're going to show you a fast marching method.
Displays it in the other screen.
Okay. So this is the original image, and then we can see the initial contour. It's just a dot. It's 1 pixel, and then it goes around and expands according to their neighboring, and then it finds the contour of our image. One problem of this method is that it always goes from an initial shape, and it also depends a lot on the location where you put it. So if you put your initial shape, which here is just a pixel, if you put it here, it's going to give you a completely different contour than what you find here. And do you have a question?
Yeah. So how that point is
Determined?
Yeah.
Well, it depends on you.
Okay.
This I just put the dot there. I selected that spot. But those are some of the weaknesses of the method. First, that you might not have just a pixel, but you have an initial shape, and then it depends a lot on the neighbors. So Dr. Nakmani, he was explaining to us that if maybe you put this dot and this dot happened to be just a pixel and it's noise and it's just white, then your contour is going to be just this pixel. So the method, it does have its limitations. And it goes from the small shape, and it goes outwards. You cannot go inwards. Now it's, I'm going to show you another example. So, this is the original image, and this is our initial contour. You can see it's a little dot underneath here, and then this is the segmented image that we get. One of the things, if we put this little dot in here around this shape, the black spot there, it's going to show you only the segmentation of this. So it depends a lot on the location and then the shape, the initial shape that you use for this.
Can you try that, or code is not allowed?
Yes, we can try.
Just find some coordinate, like
Yeah,
go this
let me
cross
move
on the
now.
figure itself. Just go this cross and pick some other coordinate.
Yeah, let me, so I can see it here
Go
better.
with a cross on the yellow thing on the top toolbar.
Oh, it's a cursor.
This one?
This
Yes,
one.
this one, and then just select something here. What coordinate is
50, 85.
50, 85. So it should be 85, 50 then. Because it's kind of opposite order. Okay, and put that as your initial contour.
So 85. Try it again. And then you can see this, the contour here.
Okay.
So let's play with it. I would put the value here, so 5560. It's gonna give you this kind of butterfly shape, which is
How about array? Array method?
Yeah, great.
let's try to put it here. Right? Yeah.
Yeah, you
You have a question?
Yeah, like, it seems to me like that equation consider the neighborhood, but when it gets to, because when it gets to one point where the shape where there is any kind of stop, it's stop to
Yes. Yes.
So yeah, that's
Once
stop
we
to
found a
control,
boundary. Yes. Yes, that's exactly right.
Yeah, because that boundary there, you know, it seems like somewhere here. When you choose one point here,
Mm-hmm.
he took this one. So it's could be, since this one he's a little lighter, you know, there's kind of stopping point, and so that's why that equation when it completes.
So I
just
don't think that
don't-
this one is technically age-based.
Yeah,
it's average brightness inside. In most cases, it has something to do with difference between the outside brightness and inside brightness. It makes kind of the blend of them as different as possible. So you're finding such a curve, which, for example, average brightness inside is as different as possible from average brightness outside that curve. Something of that kind. So you can define energies in multiple different ways. So I don't know that specific definition of energy, but you are trying to minimize some sort of energy. And this energy includes some features of the gray colors of the image itself. It could be edges related, it could be brightness related, it could be some texture related, it could be all kinds of things related. It depends on what you want to segment. So you can define the weight function and energy function which you want to minimize, and the snake, this contour, is trying to find minimum of that energy, whatever it is. Simplest example is just average brightness inside and average brightness outside. It's the biggest difference between them, like the biggest distance between those two numbers. Okay, you're trying to maximize that distance. This is one possible energy. You have multiple other kind of energies. But in that case, it seems to be something related to brightness, I guess, not
Yeah.
exactly edge.
Yeah, as long as the way the equation is defined here, as long as there is not like a huge difference in the color in this case. Okay, so if we put the here in the actual brain, then this is what it segments.
Oh,
Okay.
not bad.
Okay, and it also depends a lot on the threshold that you select. And we're gonna change it. Right now we have the threshold to 0.1. 0.01. I'm gonna change it to 0.1 and see what we get. And then you can see that it's a lot smoother. Not as sensitive.
So it also has basically penalty on how smooth your contour is based on your choice. Like if you want the contour to be very smooth, you can decide on the parameter which will give you smooth contours. And if you don't care about smoothness, then you can put the parameter to other values.
Okay. So let's go back to our we want to this part and this example. Okay. So let's go to snakes. So there are different active shape models. So we're gonna show you first snakes. This method also it's very dependent on the initial shape that you select. It's based on a spline polynomial interpolation, which is you draw a line around the snake and you want to find the shape of this. Then let's say you draw this line here, and then it's like the snake moves towards the image. So what it's gonna do is gonna show the shape around this snake, and it's very dependent of the shape that you use initially, and then of course the location where you put it. If I put this line here, it's not gonna be the same as if I draw the line in here. So it really depends. Okay, so we're going to show you some examples of the snakes.
Try to do what iteration. Okay.
This is okay. This is still running. So we'll just give it some time. So he's gonna explain better how this is calculated. But like I said, this depends a lot on the initial contour that you select, and this is taking forever. Well, because I was playing with the number of iterations, and I put 3,000. Okay.
So when she runs it again, what you're going to see is, based on her original image, it's going to start from here and the object is going to span outwards. So it will look like a snake is moving. And it's going to try to fill it into the object. That's what it's stuff is running.
Yeah.
Any questions so far?
Can you explain what is the four things are, each one?
So in a minute I'll explain it, but when trying to do the, it's called the K, the exact name, but it's called KWT for short. The external energy is all the objects is broken up. So the external energy is the energy from the exterior of the object you're trying to analyze, pretty much. This
It just vectorized the force field.
vector of the force fields, and just snake movements. So in a minute I'm about to explain this, the external energy a little bit
Yeah,
more.
we're gonna explain this part better. This is just one example. As soon as it's done running, because I happened to put 3,000 iterations, because we wanted to show how close it's gonna be. So this the original image, and we want to trace it as closely as we can. And you can see that it's curved, and we're gonna explain why it's so curved for snakes. And it's not really good at this very straight, sharp edges. We're going to explain that too.
I just try it out.
And you put as soon as it's done, because and we'll show you the things.
We have plenty more examples. So
Yeah, we have lots of samples. You can explain if you want.
how do you start this? Right. So it's called the catch. What's it? Terzopoulos model. Terzopoulos. And so we have a curve equation represented up here. It's between the 0 and 1. The reason it's between 0 and 1 because you can represent any domain or range into 0 and 1. It just depends what magnitude you're multiplying or how you alter the equation. So for example, in this slide, our curve equation is right here represented by this, I guess, blob. And our snake is represented by this arrow. And in general, the snake equation is written right here. Go on to the next slide. And so our external energy, as you mentioned earlier, is the gradient of a function, or I guess image, magnitude squared. And we use that, and we take the integral between 0 and 1. Since we're defining area between 0 and 1. And what that just means, we're just summing up all the external energies around the exterior of our object. And try to minimize this, so we're always trying to set this equal to 0. And our internal energy equation is another component, and we have two main parts of it. We have the stiffness and elasticity. As we saw earlier from our MATLAB code, it was forming curves, and every point coming to a stiff point. Part of the reason is because our elasticity is represented right there, and all this is pretty much trying to make sure get our points as close together as possible. And the only way you can keep an object as close together is the closest any object can be is a sphere or a circle. And so the reason to have such a stiff curve is because our alpha variable is higher in our beta variable. And so our stiffness function of this component is just the curvature part. Because imagine a curve being a massive half circle. The larger the circle, the straighter it will be. So being stiff, straight. So this component of our function is trying to make our snake straight, and the other component is trying to make it curve. And you adjust this based on your criteria through our beta and alpha components. And this represents just the summation, or our energy function, between 0 and 1. This is how we define it. So, for example, if you have missing data, we have a bunch of squiggly lines, unconnected. The snake equation, or KWT, is going to constrain in trying to connect our data. So that's why you see this represented like this. So it is able to fill in missing variables. Because if our equation, if you have a bunch of data like this, so our original snake is going to start moving as a circle, depending on how you draw it, and it's going to start constraining itself onto our objects on the inside of our image. So that's why it's able to fill in missing data.
Like we said, it's very dependent of the initial shape that you give it.
So if, for example, you go back, if you drew if you drew a line going across here, it probably would have not obviously formed onto the object itself because it's dependent on our initial starting points on our object, on our plane. Thank you. And so this is just an example how our variables has such a strong impact on our snake. And so if you have a large alpha, that means our object wants to be as circular as possible, trying to get as circle as a sphere shape as possible. So it's not going to conform to two spheres. While we have a small alpha, object is going to constrain itself onto the two spheres. But we also lose the ability to have straight edges. So if an object has any form of a straight edge, it's not going to conform to them. So it's always trying to find like a nice balance between the two objects, two extremes.
Maybe before you go to the actual equations, I want to clarify a little bit on the overall motivation for doing all of those snakes. So we talked a little bit already about let's move the camera a little bit. So technically, we know already about segmentation a little bit. We talked about basic segmentation and how you do segmentation with thresholding and other things. If you remember, all of that segmentation was very noisy. So if you have some sort of differences in color, it's all was based on the gray level colors. Which means that if you're using constant threshold, some of the points will be here, some of the points will be there, no relation or special relation between those points in the image. So some of them will be like one here, some of them will be one there, unrelated to whatever you want to segment actually. Because of the noise and because of uneven distribution of colors or intensities in the image. So the overall idea of snakes that you will actually localize the entire object around some initial contour. So you will, broadly speaking, outline some contour approximately, not exactly on the edges and not exactly on the stuff that you want, but then it will wiggle a little bit, it will change, it will evolve somehow, and it will catch the object somehow. So it will catch the boundaries of the object. So you'll still have this single snake, single parametric snake, you'll have single contour output. It's not like multiple points here and there outlined as one in the mask, right? You'll have single object, and it will have some specific single boundary. So this was overall motivation for snakes. Now, the problem is that edges are always very noisy, because to detect edge you need to do derivatives, and derivatives are very sensitive to noise. And this is what we don't like about derivatives. On the other hand, you don't want that snake to be like zigzaggy like that, right? So you don't want that contour to be catching every single spook pixels, which are kind of noisy pixels on the edge. Because edges, generally speaking, are very noisy in terms of derivatives, especially in terms of derivatives. So if you would catch just all of the, like, you will try to connect all of the edge points, right? Trying just to find all of the bridges between the edge points to connect them in a single contour, you would get very, very wiggly contour with a lot of zigzags, right? Because it will be very noisy. And edges look like disjoint kind of stripes here and there, white parts of the lines, right? This is how it looks like. And if you're detecting just edge of the image. If you'll connect those, still it will be very zigzaggy. Now, the idea of contours is that you can define something like that. Number one, you can define external energy, which is related to the image itself, which is lowest one when you have edge. So you're defining some function, and you have infinite number of ways to define that kind of function, which will have very, very, very low values where you have edge, and much higher values where you have something flat, something that you don't want, right? And you want to minimize that energy. So this energy, if you find the way to minimize that kind of energy, technically speaking, you'll find contour which is passing through only edges. So you'll have disjoint edges like that. Okay, you have those edges, which are whatever, and you're starting with some initial contour like that, which is closed contour. Those points will be attracted to those edges, those points will be attracted to those edges, and so on. So you'll find kind of closest edges, and most probably your final contour would be following exactly that edge, then connecting somehow to that edge, then following that edge, maybe probably something like that. Okay? But unfortunately those edges are not that clear, so if you're using actual gradient, those edges might have all kind of things like that right around, all kind of noise. Which means the thing will be going like that. I don't know, just inventing something here. So this is how it will look like, and this is not what you want. You want that smooth and beautiful contour which is passing almost through all of the edges around, right? This is what you want. Now, how can you make that contour to move the way you want? For that, you define additional energy. which will be added to the external energy based on the image, which is like something like minus magnitude or gradient. This energy dependent on smoothness of the curve itself, not dependent on the image at all. So this is second component to that energy, which you also want to minimize. So this is kind of compromise between how close you are to edges and smoothness of your curve. So this is second component, smoothness of the curve. You want the curve to be smooth, okay? If you minimize it to the maximum, it will be completely smooth, which is basically just circle or something of that kind, okay? Third component is you don't want the thing to bend too much, okay? You want it to be as straight as possible, like all of the segments should be as straight as possible. And this is basically second derivative minimization, which is exactly what you have here as stiffness. So this is bending force. You want to minimize that thing, which is second derivative of curvature of the curve. You don't want high curvature. High curvature means that basically you're trying to bend it into a straight line. Okay? You don't want that to happen. So you want to minimize that stiffness. You want actually to make some contour which is fitted to your object. Okay? So both of those, our internal energy has nothing to do with actual image. So it doesn't matter what image you have, those things will still be the same. Those are just two constants which are giving you weight of each one of them. And weight means that if you, or penalty if you like, so if alpha, for example, is very large, you are penalizing on bad elasticity, right? If beta is very large compared to alpha, then you're penalizing on big stiffness. Okay? Not giving that opportunity to go to straight line. Okay? Those are numbers that designer chooses. So those numbers are given to you to choose. Those are parameters of the problem. You don't have any classical methods for choosing those numbers. Just play with numbers until you get whatever you want. But you know, for example, if you have all kind of concavity regions or a lot of like holes that you want your snake to go into, you don't want that snake to be too smooth, right? Because otherwise it will do whatever it did with that star shape, right? It will get kind of all of the corners smoothed. You want that to be less smooth. Then you need to play with those constants alpha and beta to get enough smoothness but not too much. If you will get it a lot of smoothness, it will kind of bend all of the corners will be bent. If you give it not enough smoothness, it will go into the corners, but it will be also very zigzaggy and wavy. Okay, so you're looking for some sort of compromise here always.
Okay, so the algorithm is done running, and we're going to show you the shape of D here, and then you can see that it tries to make this straight line as curved as possible because our alpha is high on this example. Okay, this is so let's run it with maybe 200 iterations and see what happens. The thing is, I moved my up here, then it shows in the screen.
So can you change alpha coefficient to see how alpha affects the overall shape with the same number of iterations? You can also increase the step size, it will run a little bit faster.
I think it's alright. It's all.
Variable USA undefined.
No variable USA.
That's some error. It was an error. I don't know.
Look at the figure.
Hey, check the figure.
Okay, so let's close this until we can see it from the beginning.
You know, so from here, it starts with the original square block, and it just formed onto the airplane. Try to run it again. Close
Needs to
it.
close.
Okay. So we'll show you another example. With this one, active contours. The initial contour is gonna be a square. So this is a different method that we start with a big square and then we go inwards, and then we're gonna have our segmented image here. And then I'm gonna show you another example here. Actually making the mask smaller. So if we start with a smaller image, then we can see how it makes the contour. It goes inward up. It goes from the inside outside. So that's another example. And then we have here how we do the iterations. This is just another example. So we're gonna do 300 iterations. So we're gonna show the images every 50. I'm gonna close all of them. Again with the square map, the small square. So this is the last iteration, and then you can see how it goes, it expands from the initial image. Then this one. Next. And this is with their 100 iterations. I'm gonna put the other 20 in because I need to pull out the use and everything. So let's continue. Okay, so we're gonna show you this example that I just showed you guys is the these segmentation, and then we're gonna show you on this website we found how they do it. It runs in their server, so it might take a little bit. But then if we want to run the algorithms and the same segmentation that I just showed you, but now this flower. And we can see how it starts to segment the whole image. Now the advantage of this method is that how you can see here, it chooses smaller boundaries, and it's across the whole image. So if you want to have differences, and you actually want to, depending on how you want to segment your image, of course, but you can have some more boundaries, and you're not depending on wherever you put your segments.
So this one is not parametric snake. This is Chan-Besi, which is active contour which is based on level sets. In level sets, you don't have to choose a single contour. You can choose as many objects as you want. This is one of the good things about level sets. In level sets, you can define multiple initial contours, which basically covers the entire image. And this is what they do here. They just cover all the image with tiny circles. And then they basically split and blend them together in the way they want, just to differentiate between average brightness inside and outside of the image to make the biggest difference between multiple contours. So they might have not only single contour like inside and outside, they might have multiple contours, as many as you want, as many as needed. And that need will be defined automatically by the energy function, like how many you need to differentiate as much as possible between different kind of brightnesses in the image.
So, so here we changed some of the parameter, and still, like here you can see that it doesn't distinguish between these two. So you can actually, it depends a lot how you use it and the parameters here. Okay, so now let's go to dynamic templates, which is like in the video that I showed you. It's basically active contour that it moves across time. So your contour is changing with time. So like it happens with videos. And then we're going to show you another example that we found on YouTube. And then they show you how this active contours change over time. And this is how they make this faces. So this is just a long video. We're not going to show you the whole thing, but this is the basics. So if these algorithms have been used, just like in the first video we showed you, the person doesn't even have to be present, and then with these algorithms, depending on the shape of the mouth and the facial expressions, then you can make your algorithm show anything you want. And you can make people say anything you want if you trace their image, which can be very dangerous, but okay, we moved through this already. Yeah, okay, we're here. Yeah, right here.
So, can you go back a couple slides? Just a quick reminder. Level. So the main snake equation. This is our snake equation. And so this is our snake equation now in Euler-Lagrange form. The Euler-Lagrange equation, which is defined like this, which is very similar to a previous equation with internal energy plus our external energy component added to it. Get set equal to 0. And so going to gradient descent. So gradient descent is defined pretty much. You have your your function, in this case e, and you're trying to find for which iteration the path of the steepest descent of largest magnitude. So the gradient of v will provide us the path of the greatest magnitude, and we take negative, trying to find the steepest descent. We're trying to get down to the local minimum, and we're trying to get to the local minimum where it's as close as possible to 0. And probably most likely will not reach it, but we'll get as close as possible to it. And this is a simple representation where we're taking the partial derivative of e with respect to x and with respect to y. And it is important to know we have to solve for this equation, we have to set it equal to 0. That's what allows us to get as close to the local minimum. And something quick to note, when you do a gradient descent, you can get more than one local minimum. For example, we get a local minimum here, we have a global minimum on the other side. So depending on where your equation starts on the plane or on your object, your representation, you might end up landing in one of these local minimums, not the actual global minimum. So something important to just remember. Go.
Okay, so this is one example of gradient descent, is the formable templates. So our initial image, we have some parameters that we select. We say, okay, this is the iris and the pupil, and then we have this, the eye has to have this kind of shape. So we define this parameters, and then whenever we see the images, we try to fit the image to the parameters that we gave it originally, and then the algorithm is going to end up finding this with each iteration and make it as close as possible as the image here. So this is just one of the examples. You can see there, and we found it from the active controls from Blake and Pizarro. Yes.
So this is a great set, just more defined in the matrix form, so you can see what's going on. And so, for example, right here, our initial curvature equation is Ci, and when we do the changes, you can see it starts to change depending where our local minimum is trying to. So it's trying to find the greatest change. The same thing can be represented by our Fi. It's just a simple representation. We're taking the derivative of a curvature, which is equal to our derivative of each iteration. The change in step multiplied by our gradient of our actual object. And it's just something important to know is that our KWT. It's just when trying to perform this algorithm, this is just some simple guidance or steps you do when you're trying to actually try to set up your KWT. So it's important to understand, like for example, final studies, understand your tolerances, because that's one of the key things to make sure, like she mentioned earlier, once you adjust the flower picture, you might end up getting objects out that are not supposed to be in the image you're trying to target. So adjusting your tolerance is very important. And this is a different representation of our discrete energy function. It's a different representation of our previous equation, where our alphas right here, where is that you're taking the partial derivative of our image with respect to x and y, and you're adding them together. Also important to know that this first x I plus 1 minus xi is our first derivative representation of our x for representation through our x, and the y is the y component. So when we multiply by our alpha, and we go to the next part, the line below it, our beta is just the second derivative of our equation. And just so we get these following equations, and this is just our external energy component. So it's just an additional question to what's going on when the equation is running. It's pulling and pulling depending where our variables are like, trying to conform to our object as much as possible. Move on to the next thing.
Hold on.
Here you go.
Oh,
Go ahead.
Go back, please.
Go back, please.
This one?
No, the question.
Question.
This one?
No, the question.
question
The
is
question.
brain.
for it.
Oh, okay.
So what image grain force uses to hit those states not be good enough in the application? What do you think? What do you think it might not be good enough to use?
Look at the images. You have red initial contour and green final contour. Do you like it?
No.
Green
It's
one.
not good. It's missing a whole part here.
And this is what you will get from the algorithm. Do you like it?
No.
The answer is no. But why does it happen? This is the question.
You guys trapped on local minimum.
It's trapped to a local minima, and why that happens? In that case, left, like right case is difficult to say why it trapped in that specific minimum. But left case, left image is very easy to see why.
Hold on, don't answer it. Okay.
Is it because alpha is huge, the
Just
sub is huge?
some hint, okay?
Is it the color?
You have three types of energies. It's not three types. You have two types of energies. One type is external energy and one type is internal energy. External energy dependent on the image and it tries to track the image to the closest edge. Internal energy, you have two parts to internal energy. One is trying to make the curve as smooth as possible overall, like total smoothness of the curve will be big. And second is trying to minimize the stiffness of the curve, which is curvature of the curve. So as less curvy, kind of. So those are three things that we are trying to minimize. And this is what happened as a result.
I didn't get it.
Why is it? So you are trying to minimize three things with some kind of weights between them. Okay, so you have kind of weighted average of total energy. And depends on the parameters that you choose to the problem, you can weight one of them more and another less. Okay, so you give more weight, for example, to coming closer to edges, or you're giving more weight to being more smooth. But then you're losing something else. And the more smooth you become, less close to edges you become, and so on, right? So it's compromise between three different things. Thing number one, to be as close as possible to edges. Thing number two, starting from the initial contour, iterating. Things number two, to be as smooth as possible, and thing number three is to be less stiff. When you try and compromise between those three things, this green thing happens. Okay, you get the final contour which is green. So pay attention that this contour is pretty much smooth, mostly, right? Except those 2 points where you have corners kind of thing, right? But total smoothness is pretty good. Stiffness is also pretty good because the middle line is pretty straight and it likes kind of straight lines, it favors straight lines. And the circle on the upper part is pretty big, which means that also closer, like locally at least close enough to straight line, right? But edges are not that great, it's not really close to whatever we expect. Like it's close enough to the upper edges, but the bottom edge just completely missed it. Why is that? What is the energy, external energy, for those points which are somewhere in the middle of that circle? Like how you find those points? The energy is computed as minus magnitude of gradient. So what is the gradient at those points? This is the force which is pulling those points. So what is gradient in the middle of that circle?
All directions.
No. It's flat white, right? More or less. So what is gradient of flat white?
That's not, it is zero.
It's zero. No magnitude for gradient, zero magnitude. No gradient at all. Nowhere to pull that contour. So it stopped evolving there because no forces are working on that contour anymore. Because you don't have any gradient around the thing. okay, around that middle line, middle green line, right? So nothing, no forces are working to pull those points from that middle thing, because gradient is 0. Well, smoothness is good enough, and it's also not bending that much, so everything is great in terms of the algorithm. Now, the problem here is that the field, or force field if you wish, which is pulling that contour to the edges, is not reaching far enough. So around the edges, the magnitude of gradients is big, right? So gradient is high, so the magnitude of gradient is also high around the edges. But this is not reaching far enough to get to the points of the snake, because look, it starts to evolve here, right? So it starts to evolve here on those points. So you compute a gradient on each one of those points, first of all, which is those points are pulled to that edge. Those points not pulled at all by external energy because no gradient here. Those points are also not moved at all by the gradient because no gradient there, right? So the only forces which are working on those points and those points, but not on those points and those points close to the edge, are internal energy, which is just trying to preserve that as smooth as possible and as less stiff as possible, okay? For that part of the circle and that part of the circle. So this part will try to bend that way, so kind of trying to flatten that entire thing to straight line, right? And still keeping smoothness. Those things will be tried to touch to those edges because some of the forces around that edge are available from gradient, right? And those things also will try to pull up because to present straight line. Okay, so this will be kind of ellipsoidal thing which is getting like that here, and those things are more attached to here, something like that. So it will go like that. This circle will go and try to touch to that thing like that. Now, this thing from that kind of force working, getting closer to the boundary here, right? Because you're kind of making clippings at one from both sides because of the bending property, because nothing else works on that circle. You're trying to create straight line here and straight line here. This line will be just pulled out here and this line will be pulled out here. Now, those lines will be more attached to that thing. Now, what happens to those things? They are coming closer to the edge, naturally, right? When they will get to that edge, closer and closer, they will be pulled by that edge, by the external force, external energy, right? But that thing still will stay here within the white region. So it will not change at all. It will start to get kind of straight line, trying to get to straight line like that, somewhere in the middle, and not getting here at all. Like nothing is pulling anything that way at all. It should be, initial contour should be close enough to that boundary to get to them. You cannot get to the boundary without having initial contour close enough to the contour. And this is main disadvantage of that kind of parametric snake of Kasvitkin and Trezopoulos. Because if you are not initializing your contour close enough to the final contour, it will find all kind of nonsensical contours, not what you want. And this is why level sets are solving some of the problem. You have also GVF and you have all kind of other approaches to resolve and to move that field farther away. So for example, you can take the gradient field here, which is available only around the boundary, right? If you're going a little bit farther here or a little bit farther inside, no field at all. I mean, nothing is pulling or pushing in any direction from the edge because it's flat, all flat. So you can continue the same gradient also here, and you continue the same gradient also here. So you can kind of spread the field all over the place. How can you do that? Using some sort of smoothing, or you can do that using even anisotropic diffusion, which is kind of spreading the entire thing all over the place. Or you can use something which is called gradient vector flow. So this is the idea that you're starting with high vectors here, and all of the places where the gradient is very low, you're just trying to copy that vector from the places where the gradient is high. So you're kind of copying those vectors here and there and there, and so on. So you kind of spreading it on the entire image. So your external field will be available everywhere, and not only around the edges.
Should we take a break?
Yeah, sure, we can take a break.
So we're almost done with the presentation, and then we're just gonna show you guys some examples, okay? So.
Oh, it's broken.
Okay, so left here. Okay.
So, just an example, I know you've seen earlier in some of the previous images, in some other examples, our bottom left image has been our just gradients. There's been like a bunch of lines. It's just an example of our gradients, what's going on, and just where all our vectors are directed, pointing towards. As you can see, as we get closer to the edge of our object, more lines of being, I guess, for hitting our object perpendicular as we go across the edge. And here's that quick tip, just so I just want to explain.
Okay.
That's it.
We
And we have
examples.
we have a few examples still. I guess the takeaways.
Yeah. Okay.
Oh, excellent example.
There's one slide.
I don't think I can outdo this. I just give up. I'm not even gonna do a presentation now. You just outdo me. Anything I could hope to do.
That was important.
Okay, so we are going to show you again with the snakes example. If we change, what happens if we change alpha and beta? So on the original one, we have 0.02. Sorry, not this one. Alpha 0.02. And for alpha and beta. And now, so this is what we get, right? So what happens if we start changing the values of alpha and beta?
Any suggestions?
42.
40,000.
Okay, let's put, okay, which one, alpha or beta first?
Both. 10,000.
Some equal to each other.
Oh, okay. Now let's say what do you think will happen if we make beta really big? If we make it 100.
The universe will collapse in on itself.
So do you
Exactly. Whatever he said.
do you remember in the presentation where we showed you guys this equation?
Thinking before that.
Oh, was that supposed to be snakes on the plate?
This one. Okay.
More stiffness. So it'll be more straight lines. So
Mm-hmm.
we'll get
Okay.
star shape.
More straight line. But the most straight you can get. What shape is it?
The straightest are,
It's a straight line.
A straight line? Okay. On what surface?
you know, just on, when we do our shape, what's the straightest or the widest our objects can be? What? How big can
Hint.
Circle.
Okay. This
Circle.
this big?
be? About that big, you're right.
Okay.
Not this big. this
She's
big.
going
Inside
rainbow.
Inside circle.
See, and we get our objects to be more circular in shape.
So, do you guys have any suggestions? How do you play with these values of alpha and beta from this equation?
Set alpha to 312. Set beta to 2.9.
312 and beta to what?
2.9. My two
2.9.
favorite numbers.
Okay.
Okay.
That's what we get.
Thank you. Yeah,
You understand
exactly what
why?
I expected.
Yeah,
Do you understand why our this image right there is smaller compared to previously? You need suggestions? You need guesses? Why?
Shrinking to the fourth.
Yeah, because our alpha is really big, so we must constrain all our points as close as possible. And our beta is very small.
So this is the value.
She said bigger.
So what? So you flip the numbers around.
Okay.
So pay attention that the weight of the edge itself is always 1. So you're comparing those numbers compared to h, or external energy, which is 1. So how about putting them both very, very small?
Okay.
Not enough iterations. Yes.
Let's spread
400.
1,000.
Still not enough.
Still moving. Is it? It's
Yeah, it's still
Okay, still
running.
moving.
still moving.
Stop right there.
Okay, okay.
Move one.
Still running.
Oh, it's still moving.
Let me show you the other image from Pizarro.
You see, you can get straight corners. So if you get more iterations, it probably will catch you. Since the image, the original image is pretty clear.
Okay, let's do 2,000.
Just keep doing it. But I bet there is a formula that show what is the best, what are the best consideration for alpha and beta to have the.
So it depends on what kind of contour you want to get. If you want that kind of contour, you don't need high alpha and beta. If you want smoother contour, then just get your alpha and beta bigger. If you don't want those things to happen to the concavities, then change the ratio between alpha and beta.
Yeah, so
Like, larger alpha will make it kind of smaller object. Larger beta will make it bigger object. So it depends on what you want. This is just interplay between the parameters. But what you can try right now is to filter that image before you apply that function. How about in filter with low pass filter on that one, blurring the edges and making them broader. With mask of, I don't know, what is the resolution of that image? Like, how many pixels by how many pixels?
Let me see. Here.
401 by.
Okay, so let's try, for example, 20 by 20 Gaussian filter. So after you're doing I equals in double, next line I equals inf IM filter, not I am like image filter, and then open, and then we need basically image I, comma, F special, and opening function, then string Gaussian, comma, and then open square brackets, and in square brackets you have say 22. 20 space 20, and then sigma, let's put it 10 maybe,
Here?
comma 10, yes,
Okay.
something like that. Let's try that. It's still not good enough, you need bigger space. You can stop with Control C. Okay, let's take, say, 50-50, and sigma is 30.
And so 2000?
100 is enough. Let's see what we see first. Okay, can you show the real image? How do it like yeah. Okay, now go back to the previous options and alpha and beta here to 0.02 or something. Let's see how it works. No, it's missing the edges entirely. Okay, so put them 0 both.
I'm sorry?
Just 0, put them 0. Let's try to find on the edges. Both alpha also. Okay, more iterations.
Just keep going.
No, it's done. It shows the second
When
image.
is- when
We
it
just
shows
have
the
only
second-
100 iterations. Better.
It
see the
showed up
problem
this
here?
error here.
You see the problem here? What is that?
Going in and out.
What do you think it is?
Doing this. In and out.
What it means for the snake? Those are critical points. So what it means? What will happen to those points?
Well, you were
Yeah.
gonna talk. Yeah, that when it processed
Yes.
the point.
Basically,
between
this is what
the-
happens,
in
right?
the-
So
the
you
curve
had
of the
points like that. You had point like that, point like that, point like that. Okay? So this point moved here, this point moved here, and this point moved here. So technically speaking, now you have, instead of that kind of thing, technically you have something else. You have that kind of things. You have kind of triangle. This is what you see in a kind of triangle. So basically those are flipped sides. So you had points like that, and now those points actually switched around that point. What it means? What will happen to that thing? Is it important for parametric contours? Not really. Is it important for region-based contours like level sets, Derivation, and so on, where you are taking difference between internal average color and external average color? Why? Yes, why?
Because of your distances, when you're calculating the distances, it's just not going to make any sense.
No, not because of that. There is other reason. So what will happen to that thing when you continue writing the same thing.
We have a cavity.
It will grow forever, first of all. It will kind of open and grow forever. The question is why? So that loop kind of, so you created basically a loop, right? So kind of that kind of image, right? And this loop will actually grow forever based on the forces that we define. The question is why?
Is it because the pulling forces, they're supposed to be pulling to the center and actually pulling outwards?
They are not pointing to the center, they are pointing inside or outside. So what is
Inside, they're
inside and
pointing
outside
inside.
here?
Outside is nothing. Inside is
The bottom?
How we decide on what is inside? How we know that some points are inside of some curve? You have some curve, okay? This curve could be as complicated as you want, okay? Is the point inside or outside?
Inside.
How do you know?
Draw a line through the figure and see if it intersects line or wavelength.
Okay, you want that line? What line you want to draw?
Horizontal.
Okay, horizontal line.
Does it intersect any of the edges of that curve on the way out?
It's intersecting 1, 2, 3, 4, 5.
Sure, it's on the inside.
Why?
It's obvious. Yes, indeed.
Why do you think it's inside?
Because it intersects an odd
Red
amount of
has
curves.
spots.
It intersected an odd amount of curves. Or
Odd amount of curves? Yes, so it intersects odd amount of curves. How was the loop? So this is inside and outside. So what is inside and what is outside here?
inside this.
Well,
It'll
it's,
be intersecting
Inside
one
became
curve.
outside.
it's curved in on itself, so what was inside is now outside.
So this one part, this part is inside and this part is inside, right?
Mm-hmm.
But how you measure that in computer? You are not drawing that line, right? No. Computing is that way because you have parametric representation, which is just a bunch of points which are given on the curve.
You measure the tangent at any one of those points and the change in tangent.
Okay, yeah, and
You are talking of energy, no?
you are no. This is not related to energy.
Okay.
I'm talking about like how you identify for a given curve, which is C of S, which points are inside and which points are outside.
Is it the magnitude and which way is the point?
So how you identify based on all of those things.
Oh.
Each draw normal to each point on that edge, and if they're all facing out, it's the outside. If they suddenly switch to the inside, facing inwards towards each other, it's the inside.
So technically speaking, yes, you have first of all direction on that curve, right? That direction is counterclockwise. Everything which is normal direction, which is looking to the left, is inside, and everything which is looking to the right is outside. So all of those directions are inside, all of those directions are outside. And this is kind of normal to tangential line at each point. Now, look what happens here. So I'm moving with that thing that way, moving, until I get inside. Again, doing the same test.
Inside becomes outside.
So this one is inside,
It's like a
this one
Mobius
is
strip.
outside. Which means that when I'm taking average of inside and outside, I'm basically saying that this one is inside and this one is inside. No difference, right? So all of that loop makes no sense. You should shrink it to 0 because this is the same thing like this one. And it included in the average. So I will grow this thing. Because this one is my inside right now, right? When you created that loop. So this loop will grow indefinitely until it will catch some external object to whatever object you wanted. Because your original object, say, was here somewhere, okay? You wanted to catch that object, right? And it has some dark colors inside, for example, okay? And everything else around is bright. Now, when you grow in that loop,
all of that thing is darker than all of the external part, right? And then you segment it, everything works fine until you get that loop. When you get that loop, this one with this one becomes single average compared to colors here inside, which are white, right? Bright. So you will try to differentiate between bright inside and dark outside now. Because this is your outside, this is the same thing now. Which will just make the algorithm unstable and it will just blow up. And give you all kind of nonsensical results.
You test it?
Yeah, it will take time if you want to test it. You can. But you need to write that algorithm because this is not chain basic, right? This is not different algorithm.
This is nice.
You throw some air correction in there.
Okay,
Propagate
so
this.
do you have any questions? Do you want to change any more parameters?
You already want close all. That means just close. Sure, close all, right? That means just close your computer.
No.
In the future, let's have more snakes and more planes together. Actually, I have
So
snakes.
this is what's great when you have your own implementation of your snake.
Oh, I should have
You
been
can
there.
filter and save your field and not the original image. Because the original image basically you're killing your gradient and then the field which is put into the gradient locations which are high is broader, but the gradient itself is smaller, the magnitude itself is smaller, so it's not pulling the field. Right? Because of that you're losing your edge. But if you're smoothing the direction of the gradient instead of the magnitude of the gradient, just the direction, okay? And you kind of spreading that by the same filtering mechanism, right? You just spreading it around. You get much broader field, like attraction reaching, if you like. So this is also possible when you have your own implementation of the snake, but this snake is kind of closed implementation. You cannot get into the, I mean, you can get into the code, but you don't want to get into the code. This given function. Any other questions? Okay, thank you.
We got him.